Okay, let's get started. So today we're going to start our compressible aerodynamics module. There is a little bit three-dimensional viscous flow that we haven't covered, but let's leave that to the compressible section when we start to discuss swept wings, and that'll be actually a natural place to discuss actually three-dimensional viscous effects. So let's just push that off a little bit and start our compressible aerodynamics section. All right. Okay. So first, just to give you a qualitative sense of compressibility, aerodynamics actually changes very remarkably at higher Mach numbers and before you get supersonic. So this is just a very simplified geometry, just a wing fuselage combination, and we have a knockoff 4412 airfoil, so a cambered airfoil, and relatively thick. So this is the lift coefficient and drag coefficient and how they depend on the Mach number at the same 0-degree angle of attack. So what you see is that as we go from lower subsonic conditions to higher subsonic conditions, the lift first increases, right? And at some point, it drops to extremely negative values. And this is all before you reach Mach 1. And then at Mach 1, you raise the lift coefficient raise back again, but at a negative value, right? And stays more or less constant when you have supersonic flight. So in the first part of the compressibility section, we're really going to focus on what is going on over here. So let's look at qualitatively. This is at this point at the peak of the lift coefficient, right? The CP, the pressure coefficient on the upper side of the wing and lower side of the wing looks like this. So this is not qualitatively different from a incompressible flow, right? On top of the wing, you have a suction region, right? If you run X-foil, you expect to see a CP like that. Okay, so that's a highly cambered wing. And if you think about thin airfoil theory, you also expect qualitatively a pressure distribution like that. Now, this is at a slightly higher Mach number. If you look at the difference, right, you see the blue region starts to shift downstream, right? And the termination of the blue region starts to become sharp. That's when shock waves starts to happen. So when you are when the flow is flowing through a low pressure region into a high pressure region, it now forms shock waves as opposed to transition smoothly back into a high pressure region. And similar actually things happens underneath the wing, right? The region where near the leading edge you have low pressure to the mid portion of the wing when you have high pressure starts to transition as a shock wave. And this is even at a high Mach number. You can see that on the upper side of the wing, the shock wave stays there, but on the lower side of the wing, the shock waves moves downstream, right? That's what's accounting for the loss of the lift. And when you get to even higher Mach numbers, that's about 0.85 or something, the shock wave has moved to almost the trailing edge on the lower side of the wing, right? And on the upper side of the wing, it's still sitting here. That's why the lift coefficient is extremely negative over here. So in the blue region, that's low pressure, right? So instead of having low pressure mainly on the upper side of the wing, now you have more low pressure regions on the lower side of the wing. And then when you go to Mach 1, so both the upper and lower side of the wing is entirely covered by this blue region, right? And that's why the lift coefficient comes back a little bit. So we are going to get to a full explanation of what is happening, I think, in the next class or next Monday. So today we are going to start with the basics, right? Because you won't be able to understand all of this unless we first go through something that everybody hates, at least at the beginning. That's thermodynamics. Okay, so what I'm trying to do here is to present ideal gas thermodynamics in a slightly different way as you might have gone through in unified. So what I'm going to tell you is that there is the ideal gas equation, right? You need to remember and conceptualize, and everything else can be derived. And of course, the derivation will seem in the beginning more complicated than just remembering, right, the equations. But you're gonna see that actually knowing how to derive things, first of all, the derivation is gonna be useful elsewhere, but also you know exactly when the equations are correct and when it is not correct. So what is the ideal gas equation? It is the pressure equation. Pressure equal to some constant. Let me just write as R, okay, times rho times T. Right, so R is just a constant that's dependent on the what gas you are looking at. So for air, let's just say R is some constant that's independent of density, independent of temperature, independent of pressure. So this equation is less of a derived equation and more than a statement of what temperature is and what it does in an ideal gas. Right, so temperature in ideal gas is a representation of how much energy, how much kinetic energy the gas has in the random molecular motion. So think of a temperature as something that's proportional to the amount of kinetic energy or the squared velocity of the random motions. So T is going to be proportional to velocity squared of these motions. Okay. And now what is pressure? What is pressure in the microscopic sense? The pressure in the microscopic sense is basically how much force, let's say like this container gets from all the molecules bumping against the wall, right? Okay, so then if you think about what that interpretation of the pressure, how much momentum is transferred from the random motion of the molecules to the wall, right? Then you can use something actually we are pretty familiar with in aerodynamics, in the macroscopic aerodynamics, to figure out what the pressure is. So first of all, it's proportional to density, right? Because the higher the density is, there are more molecules over here, right? So on average, there are more molecules. Even if if one molecule is transferring the same amount of momentum, right, there are more molecules bumping to the wall. So pressure is going to be proportionally higher, right? So that's easy to understand why P is proportional to rho. And why is P proportional to temperature, and particularly to velocity squared? That's because if you increase velocity, increase the random velocity of the molecules, two things happens. One is that because the velocity, let's say velocity doubles, then on average, there are double amount of molecules hitting the wall per unit amount of time, right? Because they are moving faster, so there are more molecules. Even if the number of molecules are the same, the time it takes for it to bump onto the left and then bump on the right actually halves, right? So there are, the same time, there are double amount of molecules bumping. And each time the molecules bump at the wall, it transfers twice as much momentum, right? So momentum flux, as we have seen in aerodynamics, is always proportional to V squared, right? One V is how much, basically the amount of mass, proportional amount of mass going through, and the other V is the momentum per mass. So that's why pressure is proportional to density times velocity squared, right? And the velocity squared is proportional to temperature if the velocity is the random motion of the molecules. So that's basically what this equation is. P equal to basically P. I would just write it as P being proportional to rho times T, right? That's the equation I think you need to remember. And let's start with this equation and see if we can derive all the other important stuff in thermodynamics. Okay, this is simple enough, right? Okay, so the tool we're going to use for the derivation is called the fractional sensitivity. It sounds complicated, but it is really just a small change of some quantity divided by that quantity itself. in some sense, it's just the percentage change in that quantity. So for example, a change in density is d rho over rho, right? So if the density has increased by, let's say, 1%, then d rho over rho is 1%. If it decreases by 1%, d rho over rho is negative 1%. All right? And we can also have a dp over p and the dt over t. Okay. The nice thing about fractional sensitivity is that if you can write the fractional sensitivity of something, right? So let's use a familiar example. Let's use the example that of the drag on any body. Let's say drag is equal to the drag coefficient times half of rho v squared, right? Okay, and let's ask, if the drag coefficient doesn't change and density doesn't change, what is the relation of the fractional sensitivity of the drag, or dd over d, relative to a changing velocity, dv over v? So if this is constant, if this is held constant, right, you have the same air density, same object, so same drag coefficient. What is the relationship between a percentage change in velocity and percentage change in the drag? Oh, let's just try to do the math, right? So, so what is dd? dd is going to be, because of this is constant, I'll just write down cd times half rho, and the dv squared is actually 2 times v times dv, right? So dd over d is equal to this thing divided by, let's actually plug in this again, so cd over half rho, that cancels out conveniently, right? Times v squared, and that comes back to 2 times dv over v. So the fractional sensitivity of the drag is exactly whatever the exponent is on v, right? Times the fractional sensitivity of velocity. It's not a coincidence. Anything that has a power law can be, you can derive it like that, right? So what this means is that if the velocity increases by 1%, the drag increases by 2%, all right? If the velocity decreases by 1%, the drag decreases by 2%. It only works for small percentage. If the velocity increases by like 200%, this wouldn't work anymore. So that's why like you have d, like infinitesimal change, right? Okay. And if there is a cubic relationship, this is going to be 3. If this has a power of half, there will be half. Okay. So this is very useful, because if you can derive a fractional sensitivity, you know what happens on the log-log plot, right? So I'm just going to write down, I'm just going to draw this relation, right? If the x-axis is velocity, if this is velocity, and this is drag, right? Knowing that the fractional sensitivity of drag is twice the fractional sensitivity of velocity, that means in the log-log plot, any small change in any fixed change, like small delta in the x-axis, is actually the length in the x-axis is actually a fraction, right? In a log-log plot, that's like one way to interpret log-log plot. Okay, a delta, a small delta in the x-axis can be thought of as a fraction, because from here to here is actually this is maybe not the best place to draw. Let's basically start from a solid line. So any small change from here to here, that's 1%, right? Let me see. I think this line may not be actually exactly 1%. So this is 1. Okay, 1 and 2. This is actually 2%, I think. Right? Yeah, this is 2%. Okay, so any fixed length, a small length, is actually percentage increase. So if you know the dd over d is equal to 2 times dv over v, then what you really know is that we are drawing a slope of 2, right? Slope of 2. Okay, and that actually, if the slope is constant, as in this case, it is going to give you the differential relation. Is going to give you a power law relation after you integrate it. Right, so you can go back and forth. So like the tool we're going to be using is we're going to use calculus. We're going to use the fractional derivative to derive equations, and the derived equations actually reflect itself as a power law. So that's something we are going to deal with in this relation, right? So we'll start with starting from this basic equation we know previously, and ask a few questions. For a fixed mass of air, what is the fractional sensitivity of its volume to its density, right? So basically, what is dV over V has relation with d rho over rho, if mass is the same. So what is the question mark? Yes? No? What equation do we use, right? We have a fixed mass. So mass is constant. Yeah? You have an idea? 1/2? Why?
Because rho is proportional to v squared.
Rho is proportional to v squared.
Oh, no, should be minus 1/2.
Minus what?
1/2.
Minus is correct, but 1/2 is not. So what is rho times v? It's mass, right? So mass is fixed, right? So that means rho, it's just to say v is equal to m times rho to the -1th power, right? So what we have is dv over v should be equal to -1 times d rho over rho. Right? So for the same mass, if I expand it by 1%, the density is going to decrease by 1%. Right? If volume increases by 1%, density decreases by 1%. Volume decreasing by 1%, density is going to increase by 1%. All right? Agreed? So that's -1. Okay, so the answer is -1. And that means that, okay, if the x and y axis are not velocity and drag, right? Let's write it as a volume and the density. We know this line is going to be like that, right? For the fixed mass, we have a -1 slope. All right. Okay. And the next question, let's see, is at a fixed temperature, what is the fractional sensitivity of its volume to its pressure? Right, we're still thinking about the fixed mass of air. What? It's -1. That's also correct, right? Why it is -1? It is because we are now using P equal to rho RT, right? So rho RT, and RT is a constant. So that's why dP over P is equal to +1 times d rho over rho, right? And we already said that d rho over rho is minus of dV over V, right? So dP over P is also minus of dV over V. So that means, okay, so what if we change the density to pressure? Now we are seriously getting to a PV diagram, right? So, okay, so if the y-axis is pressure, x-axis is volume, then what are the constant temperature lines in the log-log PV diagram? Well, since we have at a constant temperature, right, the fractional sensitivity has a -1 relation, the constant temperature lines are lines like that with a -1 slope. Agreed? Okay, any questions on this so far? So that's just, you might have seen this before in unified thermal, right? But this is just deriving it in unfamiliar setting. Okay, good. Okay, so now we know that the constant temperature lines have -1 slopes. Next is we want to figure out what's known as isentropic expansion lines in the same PV diagram. What is an isentropic process? Okay, so this is these are something we already derived previously. Now let's consider two different processes. Both are infinitesimal processes, so that we can actually use the fractional sensitivity analysis. So process 1 is we add an infinitesimal amount of heat at constant pressure. Okay, so in the PV diagram, what does that mean? In the PV diagram, that means, use black to draw the diagram. Okay, let's like, this is both are log, right? Log diagram. Process 1 is adding at constant pressure, which means the volume is going to increase or decrease if we add heat at constant pressure. So we're holding pressure as at a certain constant, right? Volume should increase a little bit, right? So process 1 should be, this is an infinitesimally long line, but I am exaggerating. So this is process 1, right? It goes from somewhere initially to somewhere. Okay, now process 2 is a separate process. So basically we take the same amount of air initially at the same temperature, same density, right? One put it here, one put it there. And the first bunch of air I go through process 1, and the second bunch of air I go through process 2. Afterwards, because I'm adding the same amount of heat, and afterwards I'm expanding that to the same original pressure, so the two bunch of air should come to the end at the same state, right? So now let's consider what process 2 is going to be. We're adding the same amount of heat, now at constant volume. So how should the pressure change? It should increase, right? So process 2 should go like that. Now the question is, okay, is process 1 going horizontally longer or process 2 going vertically longer? Okay, anybody wants to think about how to answer the question? So which line is going to be longer? So this is only a 2A, process 2A. Yeah?
Doesn't that depend on your units?
Doesn't it depend on my units?
Yes.
Yeah, so both are log, right? Both are dimensionless. So both are fractional change in percentage. So none of them has unit. Okay, so the question is, if I add the same amount of heat, does the percentage increase in volume in process 1 bigger, or the percentage increase in pressure in process 2A bigger? Okay, use this. And this. Right, so and you remember, like, what is a CP and CV, right? So that's the heat capacitance at constant pressure and constant volume. Okay, so what is heat capacitance? Right, heat capacitance is that so it's the ratio of how much heat you have to add in for the same amount of temperature rise. All right, so a higher heat capacitance means you need to add more heat for the same amount of temperature rise, right? So air has a heat capacitance ratio of 1.4, so that's actually the case for all ideal gas primarily composed of molecules with 2 atoms, right? Like nitrogen and oxygen. So 1.4, and so CP is larger, which means you need 1.4 times more heat to raise the same amount of delta temperature at constant pressure compared to like raising to the same amount of temperature at constant volume. Okay, now that means if we add the same amount of heat, which process actually would have a higher temperature rise? Right? Is the green line has more temperature rise, or red line has more temperature rise? Yeah. Yes, the constant volume one has more temperature rise because if you look at the heat capacitance, right? The constant pressure has more heat capacitance. Means you need to add more heat to get the same temperature rise, which means that for the same addition of heat, you get less temperature rise at constant pressure, right? So that's why at constant pressure, you get less temperature rise. Now remember, what are the constant temperature lines? The constant temperature lines, let's use what color? Let's use this color. The constant temperature lines are lines of -1 slope, right? So is what I'm drawing correct? Can the two processes end at the same constant temperature line? No, right? So which line should actually be longer than what I'm drawing right now? The green line needs to be longer, right? Because the green line actually raises the temperature by more. So what I should be drawing is this. Now by how much? Right, so the delta, so this is these are raising to two different temperature lines. So the question is, what is the gap here versus the gap here? What is the ratio? Oh, the ratio should be exactly this ratio of 1.4, right? Okay, which means if these lines are actually -45 degrees, that means if they get to the same line, the length is going to be 1 to 1. And if a 1 is 1.4 times higher in the oblique direction, it has to be also 1.4 times longer, right, in its own direction, just because of these are 45 degrees. All right, so basically 2a is gamma times longer than 1. Okay, now the next question is easy, right? What is process 2b? The isentropic expansion. Basically expansion without any heat addition or subtraction. That goes from the end of step 2a, right? Goes from the end of step 2a. Let's see, I'm just going to try to use blue. End of step 2a back to the end of 1, right? Because at the end of the two processes, they should get to the same state. So the isentropic expansion should be following a line like that, right? Now, what is the slope of this line? The slope of this line is actually minus gamma, right? Because the horizontal axis, the vertical axis is gamma times longer than the horizontal axis. So, the isentropic expansion is has a slope of minus gamma. What that means is the fractional sensitivity of pressure to the volume during isentropic expansion. That's basically dP over P is equal to minus gamma times dV over V during isentropic expansion. Right? Okay. And that also means if you integrate it, what happens is the pressure is going to be proportional to the volume to the minus gamma power. Okay, and we also know that from the last slide, we also know that density and volume volume and density has a relationship of -1. That also means that the dV over V is equal to minus of d rho over rho. So we get rid of the minus sign. dP over P is equal to gamma times d rho over rho. The integral of that is going to be pressure is going to be proportional to density to the gamma power during isentropic expansion, right? So this is probably something you already have seen in unified, right? But probably not derived it. All right. Okay. Any questions on this? Okay. So we're not going to be using the integral form a lot, but we are going to be using the differential form quite substantially in compressible flow. Okay, so this is because in compressible flow, why do we care about isentropic expansion? That is because the pressure change is very fast in terms of time, right? During typical aerodynamics. So conductivity of air is actually quite poor. So for heat to go from a high temperature region of the air to low temperature region of the air through conduction takes a relatively long time. But the time it takes for air to flow from, let's say, the upstream of the airplane to a low pressure region above the wing and then to like behind the trailing edge, the time it takes for air to go through that path is actually very fast, right? A small fraction of a second. And there is absolutely no time during that time for conductivity to either add or subtract any noticeable amount of heat, right, to that air. So that's why during a rapid pressure change, like typical in aerodynamics, we can practically, to extremely high precisions, consider the process of a pressure increase, pressure decrease as an isentropic process, okay, and use this equation throughout of our compressible aerodynamics. Okay, so let's now use this equation to derive something that's new. Okay, so I want to derive what is the Mach number, right? Without telling you the Mach number has anything to do with the speed of sound. So you all know that the Mach number is the ratio of velocity to the speed of sound, right? But like, I'm not going to, at the end of this lecture, I'm not even going to tell you what is the speed of sound, but I'm going to derive a Mach number that's going to still be valid. And particularly, I'm actually going to derive the squared Mach number and essentially tell you what that means. So to start with this, we need to follow a streamline. So when we follow a streamline, right, and we define the x-axis as the direction of the streamline locally, right? So we are all doing differential analysis, right? That's basically, calculus actually simplifies things a lot when we are looking at anything complicated by focusing on a very small region, right? So everything changes only infinitesimally in the focus region. We are also able to change our frame of reference. Instead of having to have a global frame of reference, we can have a local frame of reference that's basically zoomed in and align it with the streamline. So that actually helps a lot, because the equation, the momentum equation, which in a global frame of reference is three-dimensional, now becomes just the one-dimensional. So dP over dx is the pressure force, right? Again, like we are now simplifying things by ignoring viscosity. So the only force over here is pressure force. So negative dP dx is the pressure force per volume, right? So so the pressure force per mass is this divided by rho, right? This is pressure force per mass. Okay, and the pressure force per mass is acceleration, right? That's equal to acceleration. which is equal to du over dt, where the d is the material derivative. So if we follow a particle along the streamline, how fast is the velocity changing, right, as we follow it. Now, in a steady state flow, right, what is du dt? Du dt is basically a u times du dx, right? That's because as we follow a streamline between two different times, we're actually traveling in space, right? We are looking at how much the velocity is different over space, actually. And the ratio of a dt and a dx, so basically u itself is the ratio of dx over dt, right? I mean, we can write it like dx over dt. So that is why the du over dt can be translated into u times du over dx. Okay, make sense? So that's why we are deriving this equation, right? So in a steady state flow with viscosity neglected, right? So if we move this to the right hand side, negative dp over dx divided by rho is the acceleration, which is equal to u times du dx. Okay, good? Okay, so this is the equation we're going to use to derive what Mach number is. Okay, so yeah, so first of all, let's just copy what we derived previously using thermodynamics. So what we derived previously is we wrote in blue the sensitivity of pressure to density is dp over p is equal to gamma, actually 1.4 times d rho over rho, right? So like, yeah, so that's going to actually be plugged into this equation. So this equation actually tells us what is the relationship between a changing pressure and a changing velocity. And also there is a density in it. So what is the fractional sensitivity of density to flow velocity? So let's actually combine the blue equation with the black equation to derive that. Let's actually divide to actually get a to fractional sensitivity, right? Let's divide this equation by p on both sides. So we have rho u over p times du over dx plus, let me just look over an infinitesimal x, right? So let's just look over 1 point and a small delta over like downstream of the line, and so that's actually just going to be du. So plus a dp over p, right? That's equal to 0, right? So that's directly from this equation. And what that means is that we can substitute dp over p with gamma times d rho over rho. So rho u over p times du would be plus gamma times d rho over rho would be equal to 0, right? Okay, so good so far. And then let's also translate this du into fractional sensitivity. So we divide a u here and put a square over here. All right? So basically that relates the fractional sensitivity of velocity to a fractional sensitivity of density. So now let's answer the question, what is the fractional sensitivity of density to flow velocity? We can write as d rho over rho, put it on the one side of the equation. It is going to be equal to, we need to divide both sides by gamma, right, 1.4. This is going to be equal to minus rho u squared divided by gamma p times du over u. Okay, what that means is that if velocity increases by 1%, density would drop, but by what percent? By this much percent, right? And let's just call this number as m squared, okay? it turns out to be square of the Mach number, right? It turns out you can just say the rho u squared over gamma p is equal to the square of u divided by square root of a gamma p over rho, and square root of gamma p over rho turns out to be the speed of sound. But let's talk about that later when we start to talk about unsteady flows and acoustics. And now we don't even care about this number being speed of sound. Let's just think about this quantity, right? We call the squared Mach number. So what this quantity is the fractional sensitivity, right? When we have extremely low Mach number, let's say Mach number 0.01, the squared Mach number is going to be 0.0001, right? It's almost negligible, which means if the velocity increases by 1%, the density would decrease by, I don't know, 10 to the minus 6. So basically negligible, right? Okay, and but as the Mach number rises, and particularly, let's actually think about the squared Mach number, because the Mach number actually doesn't, it's not, it's more difficult to think about than the squared Mach number. If the squared Mach number becomes 0.5, it is already significant, right? Velocity increasing by 1% means the density decreasing by 0.5%. It's noticeable, right? So remember, like when we were visiting the wind tunnel, I was asking a question, okay, the contraction, remember the contraction has a ratio of 8 to 1, right? Okay, how much does the velocity increase, right? A lot of you answered, okay, a ratio of 8, right? Because you use conservation of mass. And if the density did not change, right, then the area times velocity is going to be exactly the same here and here. So if the area decreases by a factor of 8, the velocity would increase exactly by a factor of 8. But that's only for incompressible flow. And for compressible flow, the velocity would increase by more than a factor of 8 because the density would drop, right? But at that time, we have no instrument of answering how much does the density drop, and therefore how much does the velocity increases beyond a factor of 8. And now we have the tool of answering this, although it's going to be a differential form, right? So we haven't integrated this yet. So we would only know that, okay, if the area decreases by, let's say, 1%, okay, in incompressible flow, the velocity would increase by 1%. All right, but if the velocity increases by 1%, according to this, right, at a Mach number of 0.7 something, let's say m squared equal to 0.5, the density would actually decrease. If the velocity increased by 1%, the density would decrease by 0.5%. Okay, then as a result of a decrease of area by 1% and the increase and the decrease of density by 1%, the area times density would decrease by 1.5%. So the velocity would have to increase by 1.5%. So things doesn't work anymore, right? So that's basically tells you an example of how we can do this. And particularly, let's answer this question: what is the fractional sensitivity of mass flow per unit area to the flow velocity, rho times u, right? Because this, let's see how much time, yeah. So this number is critical in mass conservation, right? So rho u, so in compressible flow, we have u times area equal to a constant. That's steady flow mass conservation. But in compressible flow, rho is a variable, so rho u times area is equal to constant. So what is the fractional sensitivity of what is d rho times u divided by rho u? Okay, so now we can also work this out. It's actually easier than you think. The fractional sensitivity of a product is actually equal to the sum of the fractional sensitivities. It all makes sense when you think about the logarithmic. Okay, so let me work this out in this way. D something over something is actually d log of that thing. Agreed? That's basically the derivative of a logarithm. And the d log of this is basically d log of rho plus log of u, right? Okay, and the d log of rho is d rho over rho, d log of u is du over u, right? Okay, and now let's use what we had before. D rho over rho is minus Mach number times d over u. So we have minus Mach number du over u plus du over u. Sorry, that should be du over u plus du over u. So that's basically, let's just collect these terms. So that's 1 minus Mach number square du over u. All right, so again, if Mach number is 0, we covered the previous result, right? A fractional change in the mass flow per unit area is equal to the fractional change in the velocity itself, compressible flow. But if Mach number squared is equal to half, then as velocity increases by 1%, the mass flow per unit area only increased by 0.5%, right? Okay, that also means, think back on the wind tunnel case. If the area decreases by 1%, that means not velocity has to increase by 1%, but the mass flow per unit area has to increase by 1%. Okay, that means at a Mach number square of 0.5, the velocity has to increase by how many percent? If the area decreases by 1%, 2%, right? So basically, if area decreased by 1%, this thing has to be minus 1%, right? And if this guy is half, this has to be, sorry, if area decreases by 1%, this has to be positive 1%. And if this is half, du over u has to be 2%. All right. So for the same amount of a decreasing area, the velocity increase has to be more than was before. Okay, right? So that translates into the last question, right? Considering conservation of mass, the fractional sensitivity of stream tube area to flow velocity. So if you have a stream tube going like this, right, the area decreases. The area over A is going to be equal to 1 minus m squared du over u. All right. Okay. So there is a strange thing here. So when Mach number is less than 1, right, as you increase in velocity, the area required actually shrinks. Makes sense, right? But as Mach number exceeds 1, the relation becomes the other way. As you increase in velocity, the area required actually increases, right? It makes sense through the derivation, because as you further accelerate in a supersonic flow, the decrease, yes?
Well, I'm just going to ask, why is it 1 minus m squared, not m squared minus 1?
Oh, yeah, it's minus. Yeah, thank you. M squared minus 1, right? It's m squared minus 1. So negative of dA over A. That's because rho UA is constant. Yeah, thanks. So that means A is equal to, A is proportional to 1 over rho U, right? So that's the fractional sensitivity of A is going to be minus 1 times the fractional sensitivity of rho U, right? Thank you for pointing out. Yeah. So, yeah. So essentially, so first of all, the relationship reverses in the supersonic flow as you accelerate further in supersonic flow. The density drop is now more significant than the velocity increase. Okay, so at supersonic flow, the drop of density when m squared is greater than 1. If the velocity increases by 1%, the density drops by more than 1%, right? That means rho u would actually drop as velocity increases in supersonic flow, and the required area actually increases. Second thing is that even restricted to subsonic flow, right? So if the streamline contraction is going to be the same, the increasing velocity actually has to increase as the Mach number increases. And if the increasing velocity increases, the decrease in the pressure would also be more significant, right? So that actually helps explain the first portion of the increasing lift coefficient. Because as the Mach number becomes higher and higher, for the same, let's say, for the same geometry of stream tubes in the area, right? If I go from here to here, the stream tube contracts. And if I have a higher Mach number flow, the velocity increase here has to be even higher than for incompressible flows. And as a result, the suction peak, like the lowest pressure region, is going to be even lower pressure compared to incompressible flows, fractionally, right? And as a result, the lift coefficient actually would keep increasing as you fly at higher and higher Mach numbers until shockwave develops. And that's something we'll discuss at the next lecture. All right. I'll see you Friday.